my job is a little unique. It's not like your standard, I write code and go home kind of thing. I work for a very large machine, a world-class machine that essentially is called the Synchrotron light source. Those of you that don't know what that is, which probably most of you don't, it's basically a large microscope. It's a large machine that produces a very small amount of wattage at very high energies. So essentially, what I'm going to lecture just like that. So the ring here this is a very large ring. It's almost a mile. And what happens is if you have a beam of electrons that runs in the circle in the storage ring, right? And what happens is that as the electron beam bends, it emits light to what we call beam lines. So all these beam lines are different. They're for different energies and for different scientific experiments. Some are doing structural biology, some are doing material science, some are doing soft X-ray, some are doing hard X-ray, some are doing infrared. So as far as the science goes, that's not really my job. I talk to a lot of scientists all the time, and they do cool stuff. But generally, my job is a couple of things. One is to keep the thing running. Okay, so there's a maintenance aspect. I guess I'll actually this. One is a maintenance aspect, where I basically keep the machine running, make sure it's running smoothly. The other is I do development projects for the accelerator. So they'll want different magnet systems to do different things. They're constantly upgrading it. And I also do designs for other systems in the United States and elsewhere. So it's a very spread out job. But essentially what it does is, what I like about the light source is that you can do a lot of parallel science all at the same time. And part of it is like I feel like I'm giving back to the community, giving back to humanity, because all these people are super duper smart that are at these beam lines. They normally have 3 to 5 days of doing experiments, and they write papers based on that data. And it runs 24/7. So if the beam doesn't operate properly, those people don't get to do their experiments. A lot of times when called in the middle of the night, there's something called a beam dump where we basically lose electron beam, which means we lose light, which means everybody's experiments stop. So there's a lot of responsibility on the electrical engineering team in particular to keep things running. And there's a lot of other groups at NSLS II. So I sort of catered this presentation for just electrical engineering, but what I do, but there's so many groups for NSLS II. It's radio frequency, which is a very, very important group. There's the electrical engineering group, which basically handles power supply systems for the magnets and the controls. There's the beam position monitor group, which uses very high precision devices and detectors to look at where the beam is so that we can have closed loop feedback on the whole system. What's really amazing, many amazing things. If you ever take a tour of this place, I highly encourage it. It will blow your mind. You'll never know what anything is. I mean, I can work here for 40 years and I still won't know everything about the place. But essentially, it's a lot of feedback systems all working together and then maintaining stability for extremely long periods of time, which is pretty incredible. As far as a large engineering feat, it's phenomenal. I sort of joined after it was kind of up and running, and I replaced a bunch of retirees. But the guys that really built this place really know what they're doing. All right, so how does it really work? This is a very simple thing. There's a lot of physics that go on. One of the niceties of being in this department is I do get to go to something called accelerator school, where you have the opportunity as an engineer to learn the physics of the system, which is nice. A lot of it is over my head, frankly, but I get drips and grabs. Essentially what happens, how do we make an electron beam? Just really quickly, we have a LINAC. So basically, you have a little emission of electrons that is accelerated to a linear accelerator. Then this circle, the small circle, is a booster that boosts up the energy to 3 gigaelectron volts of our system. And then it runs in the storage ring, which is this large outer ring. And here, what's really nice is they show you the dipole magnets. Essentially, we all know from basic physics that, if you have a magnetic field, the electron will follow in a circle. So what we're doing is we're basically trying to bend the electron beam so that the light comes out and we basically illuminate the beam. This entire system has magnets lining it. So there's solenoids in the LINAC, there's a bunch of correctors and dipole magnets in the booster, and the larger dipole magnets on the outer side. There's corrective magnets, there's all different types of magnets, all different sizes, and all of them meet different types of power supplies. The booster is probably the largest power supply. It is a ramping power supply, so it injects electrons into the beam every 2 minutes or so. The dipole power supply maintains all of the current in all of these magnets. These magnets bend the beam at 6 degrees, and there's 60 of them to make 360 degrees, and they require a very large amount of current, and basically just maintain stability of the beam as well as bend it. So